force parallel is number 2.
Okay,
It's working.
so let's start with the first incline plane lab. So we're going for board, okay? So I promise you, on the test tomorrow, there's gonna be incline plane problems. So what are the three that are always present? Yes, Avery, dude, I'm recording this live for you, okay? Watch out. So what are the force parallel, which is always gonna act which way? Down. Okay? Always acts down. Now, it doesn't always have to be negative, doesn't always have to be positive. It depends upon how you define your system. Okay? I don't care about the sign. Hey, let's get the number. Now, how do you calculate force parallel? FG sine theta. So if you're on a flat surface, you're taking the sine of 0, which is 0, so there is no force parallel. You go to the extreme and you tilt something up into 90 degrees and you go like this, then the sine of 90 is 1, then your force parallel is your gravitational force. Okay, so you can go from 0 all the way up to, hey, it's the same as your gravitational force. So, Nick, what's another one?
Force gravity.
Which is always going to be what? Times your mass. Okay? And again, don't worry about making that positive or negative, just get the number. Okay? Because that's what you're going to use to calculate everything else. Now, there's one more. Braden.
Force normal.
And how do you calculate that?
Force gravity, cosine theta.
Now, here's what you're going to do wrong. And you're going to have friction on an inclined plane. And you've got to take mu times force normal to get force friction. And you've got to use the normal component. You just can't use the mg. You have to use that side of the triangle, which is what some people did on the assignment that I just gave back. Not to mention any names. But you have to use the force normal. Now, if there's friction, Kellen, will friction always act up the inclined plane?
No.
No. Which direction will it always act?
Opposite the direction of motion.
Beautiful, okay? So if you're pulling it up the inclined plane, friction's going to act down the inclined plane. If you're letting it slide down the inclined plane, friction's going to act up the inclined plane. So, the beginning of the lab, you're trying to find the coefficient of static friction. So you took a block, set it on a board, you lifted it up. Now, this is the quintessential example. There's forces acting on this block, but what's the acceleration? Do not make this difficult. Zero. It's not. There is no acceleration. So if I ask you on the test tomorrow a multiple choice question, and I say, hey, you're applying a force of 5 newtons, but the frictional mafia has a value of 10 newtons. And I say, what's the acceleration? It's very, very possible that your acceleration is just 0. Because if there's a 5, you're only applying 5 newtons, and the frictional force is 10, it's a very real possibility that you just don't have an acceleration. And that's what's happening right here. The gravity mafia is trying to drag it down. The frictional mafia is holding it in place. Obviously, the frictional mafia is winning at this point because of the fact that it's not moving. So just because I tell you, hey, here's the force, what's the acceleration? It is very possible that you don't have an acceleration. So don't flip out if that happens. Don't go, oh my God, force equals mass times acceleration. But that's only going to happen if the force is big enough to make it move. Okay, so I lift it up, I lift it up, I lift it up. At some point, that just begins to slide. And so that's when we came up with that equation that mu equals tangent theta, but that only works for static friction on an inclined plane, okay? That only works, it's a one-trick pony. It's a cool trick, don't get me wrong. But unless I specifically tell you, hey, let's calculate the coefficient of static friction on an inclined plane, that's the only time you use this. It is a absolute one-trick pony, okay? But if it's moving at all, you can't use this. So I would have to specifically tell you, calculate the coefficient of static friction on an inclined plane. Boom, you take the tangent of the angle, that's all you have to do. All right. Now, the next one. You set up an inclined plane at 30 degrees. So Jane Carroll, your diagram is going to look something like this. Okay? You're going to have a 30-degree angle. Okay? Draw a horizontal line. Measure up 30 degrees. Measure up 30 degrees. You're not just going to randomly draw a triangle. You take your protractor, you measure up 30 degrees. So your FG, that's just the weight of the block. You hung it up. Boom, you have that number. Okay? Your force normal, you're going to calculate that by taking FG cosine of 30. You're going to get that number. You're going to have your force parallel. You're going to calculate that number because by taking FG sine theta. So here's a simple way to see if your force parallel is correct. Take the weight of your block, divide it by 2, see if that's your force parallel. Okay? That's it. Because sine of 30 is 0.5. So if you want to see if your force parallel is right, take the weight of your block, divide it by 2, see if that's your force parallel. If it does, hey, you're right. If it isn't, something has gone horribly wrong. Okay? So literally, take the weight of the block, divide it by 2, that should be your force parallel. But that only works on a 30-degree angle. Don't think, oh, that always works. Here's how I get force parallel. I just divide by 2. No, that only works because it's a 30-degree angle. Now, here's the other thing that you should have, pointing down the inclined plane. As a separate vector, somewhere you should have your force friction, okay? Now, you have to decide how you want this system defined. Jackson, let me see the paper. This one. So, if Jackson is going to say, which in this case he defined downhill as being negative, like when I look at that force parallel, which is right, he should have a negative number, okay? Because that's how he defined his system. Now, if you're 1G and you said, no, I want downhill to be positive, that number would be a positive value. I don't care how you define the system in this particular problem. That's up to you. But if you tell me you're defining downhill as being negative, when I look at that force parallel, that better be a negative number. That's the whole point of how you define the system. Now, here's going to be the most important part. Jackson. Which direction is force friction going to act, Jackson?
It'll be going, or it's just the opposite of the direction of motion.
Okay? So here's your 30-degree angle. You're pulling it up the inclined plane. Which direction does your force friction act?
Down.
So what should, on your system, what should your value here friction? Should be a negative value. According to you, force friction is pushing it up the inclined plane. Yeah, that's bad. Yeah, that's bad. That's different. Let's change it. Okay? Okay. Now, here's the most important thing. Let's just say that your force parallel was negative 2.5 newtons. Okay? Just make up a number. Now, let's say it's negative 2.5. And you define downhill as being negative. And let's say that you measured that force applied, which in Jackson's world is going to be a positive number. And let's say that's 3 newtons. Okay? I'm just making up numbers. So here's the first thing I'm going to look at when I look at this diagram. Your force applied, which is 3 newtons in this case, and your force parallel and your force friction better add up to equal to 0. Okay? So if this is 3 and that's minus 2.5, Jackson, what would the value of your force friction be?
Couldn't hear if person was talking to me.
Jackson,
Yeah.
you owe me $3.
Yeah,
You paid back $2.50.
yeah,
How much do you still owe me?
0.5.
Half, right?
Yeah,
So here's what I want to see. In this case, it's going to be negative. So here's how you can check that this is right or wrong. Take that applied force going up, okay? So, let me see the sheet again. So, on this top right corner where it's force applied, Jackson has 2.61 newtons. So, when I take his force parallel and his force friction, those two numbers added together better add up to that force applied. Okay? That's how you can check that this is right. Take your force parallel, take your force friction, add those two numbers together, those should add up to your applied force. Okay? If they did, hey, you're okay. If they don't, that's a train wreck. Okay? That's the easiest math you're going to do. Take your force parallel, take your force applied, your force friction, add those together, see if you get your applied force. Easy peasy, lemon squeezy. Okay? So, you should have, on this diagram, there's certain things I should see. I should clearly see 5 different vectors. The weight of the block, the normal, the applied force, the force parallel, and the force friction. I should clearly see 5 different vectors. Do not combine your force parallel and force friction into one big vector, okay? They're two completely separate vectors. Okay, you can draw them end to end. You can draw your force friction as a separate line. I don't care. But again, here's what I'm going to look for. Do these two values here add up to that force applied going up the hill? First thing I'm going to look at. I should also see the scale. Did you let 1 centimeter equal 1 newton? Did you let 2 centimeters equal 1 newton? Just don't randomly draw lines and go, oh, it's okay. It's all good. I'll just randomly draw a length of a vector. No. Okay? You have to say what the scale is. That's the whole point of the vector diagram. Okay? So when you get to the questions down below, question number 1, you want to know how much force is applied. Basically, you're going to calculate your force friction and your force parallel. Both of those are acting down the inclined plane. So your answer to question number 1 down below, this is an ish, but it should be in the low 20s. Okay? What do you have? Not in the low 20s. What do you have?
Low.
Huh?
Low.
Low? Like low 20s or lower than 20?
Lower than 20.
Okay.
A lot lower.
Yeah, that's bad.
And the negatives. -5.
Well, it's just, how you define it doesn't matter, but it should be in the low 20s. Could be positive, could be negative, depending upon how you define your system. Okay? Now, number 2 works the exact same way as number 1 is. You're going to take your force parallel, add it to your force friction, and that's going to get you your applied force. But here's what's different. You're tying a weight on the end of the string to provide that force to pull it up. So to get, on number 2, you're going to find your force. In newtons would make it GPA, okay? Somewhere between 3 and 4. So the force that you need on number 2 should be between 3 and 4 newtons. To get the mass, you're going to take that answer and you're going to divide it by what, 1G?
9.8.
Beautiful. So you're going to take that force, let's say it's 3, let's say you think it's 3.5 newtons. You're going to take the 3.5 newtons, divide that by 9.8 meters per second squared, there's going to be the mass that you're going to need. Now, when you do number 3, the only difference between number 2 and number 3 is that on number 3, you're letting the block slide down the inclined plane. So, Grace, if the block is sliding down the inclined plane, which direction is friction going to act? Opposite way. So on number 3, now you have 2 forces acting up. Your applied force acting up and your force friction acting up, which should equal the only force acting down, which is the force parallel. Okay? So on number, you don't have to do any new calculations. You're just going to change the sign in your force friction. So on number 3, the force should be between 1 and 2 newtons. So your overall answers on number 2, this is an ish, okay? That first mass on number 2 should be around 0.4 kilograms. And on number 3, that mass should be around 0.2 kilograms. Okay? So number 1 on the 3 problems down below should be in the low 20s. Number 2 should be around 0.4 kilograms. Number 3 should be around 0.2 kilograms. And then you should have that diagram with the 5 forces. You can draw that on the back. You can do that on another sheet of paper. I don't care. All right. Any questions on the blue sheet? Everybody cool? Know exactly what I want. Okay. Now, as a completely separate lab, let's talk about the salmon colored lab. And yes, it's salmon colored, it's not pink. It is not, it is so not pink.
All day long.
All day long, no, you're colorblind.
Minus 10.
Absolutely, if not 15. Okay. Now, I promise you, on the test tomorrow, and we'll go back and do a demo with this, you're going to have a question relating to this magnet portion of this lab. I promise you, okay? It's going to happen. It's going to be the second to the last problem, top of the last page. That's where it's going to be. So, here's the whole point. You guys had a flat surface. No, you guys had an incline. You guys had an incline. Erase. So you guys had an inclined plane, and the first thing you did is that you just let it roll down the incline. So, Jaden, assuming that it is a frictionless surface, what's the only force acting to make that thing move down the inclined plane? It's either forced normal gravity or forced parallel. You got a 1 in 3 shot. Beautiful, okay? Because when you put it on an inclined plane, that's what the gravity mafia is trying to do. The gravity mafia is trying to make you move down the inclined plane. Now, just because it's going to make it easier for me to grade, notice at the top of this lab, I tell you exactly how I want this system to define. You all don't get to vote, nothing personal. But I'm telling you, anything going down the inclined plane is negative, anything going up the inclined plane has to be a positive value, okay? Downhill is negative. So obviously, what has to be the sign of your force parallel? Landon.
Negative.
Negative. Because that's what's acting down the inclined plane. Your force parallel is not making you go up the inclined plane. Your force parallel is acting down the inclined plane. So you know your force parallel is going to be a negative value. So when you look at your answers of force, net force, and acceleration up there on the top, okay, this part right here, you should have a bunch of negative answers because that's what's acting down the inclined plane, okay? That's the only thing you've got, is everything acting down the inclined plane. So all of your answers, force, net force, acceleration, all of those should be negative values because that's acting down the inclined plane. So you set it up, you measured your times, okay? Typically, and this is an ish depending upon your angle and some other stuff, typically those times are around 1.5 seconds, okay? It's a ballpark, right? Typically it's somewhere around there. You need to calculate the experimental acceleration using displacement on time. So on number 8, you know distance equals 1/2 AT squared plus V naught time. You're clever. What did you let the initial velocity equal, Kendall? 0. So, Kendall, solve that for acceleration. And I hate fractions. What are you going to do?
2d over t squared.
Beautiful. 2d over t squared equals a. I should see that calculation. Your displacement is going to be the 0.4 meters. Take your average time, boom, you get an experimental acceleration. as a ballpark, and this is a huge ballpark, your experimental acceleration is typically somewhere around negative 0.4. Okay? That's an ish, but it's somewhere around there. Obviously, it's a long way from 9.8 meters per second squared because of the fact that it's a very shallow angle. Okay? So that's typically ballpark around negative 4. Okay? So what you're saying is that you have this force parallel, the gravity mafia, trying to drag this thing down the inclined plane. Cool, you got these times. Now, the next step is that you put a magnet in here. So due to the magic of electromagnetic theory, which I won't bore you with an entire lecture on, the short version is Mother Nature doesn't like the change induced by the magnet. Mother Nature goes to these aluminum plates and goes, hey, we're going to work against this. We're going to be cool. We're going to create our own magnetic field that opposes that magnetic field. And so because they're working in opposition, the magnetic field created in the aluminum plates works against and provides an opposing force that acts against the downhill force. So listen to me, listen to me, listen to me. Whenever you have a magnet, and you're going to have this on the test tomorrow, you mark my words, anytime you see the force in that magnet, it's going to work in the opposite direction that the cart is moving. Okay? Always. No exceptions. None. Zero zip. The magnet will never, ever, under any circumstance, because that would violate any number of laws of physics, work to make the cart go faster. So when you see a problem, you see that magnet, right away you go, ooh, that force has to be acting in the opposite direction. So in this case, you have the magnet going down, or the cart's rolling down, which means the force from the magnet has to be acting up the hill. So I don't know what the force from the magnet is, but I do know it's going to be a positive number, because that's acting up the hill, and we're defining everything as being down the hill. So, then you're going to time it with the magnet inside. Hopefully, that time is bigger than the first set of times. Typically, that's around 2 to 2.5 seconds. Okay? All right? So, with the magnet in there, you should have seen longer times. Morgan, did that happen? Okay. So, again, now you're going to calculate a second acceleration. So, on that back side, on those net force calculations, on that number 5 on the back, again, you're going to use 2d over t squared equals your acceleration. Distance is still 0.4 meters. Now you're going to use the time with the magnet in there, and you're going to calculate a second acceleration. It's still going to be a negative value because it's still going down the inclined plane. So hopefully what you should see is that when you compare the acceleration on the front on number 8 to the acceleration on number 6 on the back, or excuse me, number 5 on the back, the one on the back is going to be a smaller negative number than the one on the front. Okay? If you didn't, you broke physics. Okay? That's bad. Now, here's the trick. The whole heart and soul of this is number 7. Using the force parallel and the net force just determined, what is the value of the opposing force created by the magnet? So, if you look at force net equaling force parallel plus the force from the magnet, okay? There is no applied force. We're not dragging it. There's no squirrels. Nothing's pushing it. There's no weights attached to it, which is dragging it. These are the only 2 games that you have in town. Remember, I beg of you. Of these 3 forces, what's the only one that equals mass times acceleration? Net force. That's it. So, to get this number, you can take the mass of the cart, multiply that by that. To get your answer to number 6, you're going to take the mass of the cart, which is usually about 1 kilogram, and multiply that by that acceleration on number 5. Typically, that's around negative 0.2. So in round numbers, here's what you have. You're trying to solve for the force from the magnet. That's what you're trying to find. So that net force is approximately, and this is in very, very, very round numbers. The force of the magnet is about negative 0.2 newtons. The force parallel in very round numbers is about negative 0.3 newtons. So if the force parallel is negative 0.3 and the net force is negative 0.2, Madeline, what's the value of the force from the magnet? No, look at these numbers. This is negative 0.2, this is negative 0.3. What do I add to negative 0.3 to get to negative 0.2?
0.1.
Beautiful. 0.1 newtons. Okay? So the force of the magnet in very round numbers is going to be about 0.1. It's going to be a positive value because that's acting up the hill. So here's how you can check that your answer to number 7 is right. Take your net force that you have on question number 6 on the front, negative value. Subtract out the negative of your answer to the second number 6, so you can have like minus a negative, and then that should get you the value of your opposing force, which should obviously be a positive value. Cool with that? Okay, that's what you got. So, on your diagram, this is going to be a very shallow angle, okay? Whatever your angle is, 2 degrees, 3 degrees, whatever that is, it's going to be an exceptionally small angle. So you're going to have, you can just draw a box, so you're going to have your FG, your force normal, the force from the magnet, and your force parallel. Okay, you should have 4 forces on there. So here's the story. That force from that magnet better be a positive number because that's what's acting up the hill, and your force parallel should be a negative number. But these are vastly different scales. So that's why I said you want to let this gravitational force here and that normal force, which are probably going to be around 15 newtons, okay? Maybe you let 2 newtons equal a centimeter, okay? Where you divide that by 2 to get the length of that vector, or you can just let 1 centimeter equal newton. But certainly on these, those are going to be really, really, really small numbers, like 0.3. If you try and draw 1.3, it's going to be horribly difficult to draw and very annoying for me to look at. So certainly on this, at least let like 2 centimeters equal newton. If not, let 4 centimeters equal newton. So here's what I should see. Somewhere you're going to say, for my FG force normal, so many newtons equal a centimeter. For your force parallel and the force from the magnet, you're going to say so many centimeters equal a newton. So I should see 2 distinct scales. What happened on your FG and force normal, and what happened on your force parallel and the force from the magnet. Okay? Do not draw this on the same one that has a 30-degree angle from the inclined plane lab. These are 2 completely separate labs. Okay? Do not staple the 2 labs together. They are completely, these are going in as 2 completely separate labs. Okay? Now, if you want to hold on to these and hand them in tomorrow for the test, you can. If you're done with them and you want to get them handed in, that's cool too. Any questions on the salmon lab? Cool, going once, go twice, so. Lauren, stop you on the camera, please.
Put them on the same page.